Liquid Air and the Liquefaction of Gases. By Thomas O'Connor Sloane. All books on this channel are in public domain. Preface. In Gulliver's veracious account of his travels, we read of the work done in the famous Academy of Logadoo. In one department 50 men were at work under the superintendence of the universal artist, as one of the illustrious investigators was called. These men were engaged in various occupations. Some were condensing air into a dry tangible substance by extracting the niter, and letting the aqueous or fluid particles percolate. So says the great Dean. Selecting the solidification of air as one of the impossibilities worthy of embodiment in his sarcastic romance. During the present generation the triumphs in natural science have been most wonderful. The prosaic narration of what has been done sounds like the romancing of a Cyrano de Bergerac. We read of the hardest metals, such as iron and nickel, carried off in the gaseous state by carbon monoxide. The surgeon unconcernedly has the interior of his living patient's body photographed. The triumphs of chemical synthesis culminate in the production on the scale of manufacturing industry of a hydrocarbon from coal and water. Marconi follows a yacht race and telegraphs its phases to the distant shore over miles of water, without a wire. And today air is liquefied by the gallon. Hydrogen and helium succumb to intense cold, becoming mobile liquids, and the last miracles of science may figure among her greatest. The present work aims to tell the history of the liquefaction of gases, wherein the physicist has exceeded the fictitious achievements told of in Gulliver. The subject, extending over a century, is full of interest from the biographical as well as scientific standpoint, and it is hoped that the presentation of it with such scope will be acceptable to the reader. For assistance in the compilation, the author's thanks are due to many. His requests met with quick response from such men as L. P. Cayetet, Henri Dufour, Charles E. Tripler and James Dewar. And a personal friendship brought about by this book has fully justified the labor of writing it, the friendship of that wonderfully endowed scientist Raoul Pictet, one of the fathers of liquid air. Poet, musician, physicist, chemist and mathematician, a veritable admirable Crichton. The work is but begun, the future possibilities are great, and it is impossible to foresee the impending developments in the liquefaction of gases. Liquid Air and the Liquefaction of Gases. Chapter 1. A question has often been asked latterly. It is, what is liquid air? The subject has been so much discussed, and so much has been made of it, that it is hard to believe that there is not some occult mystery attending it. Liquid air is simply air which is so cold that it assumes the liquid state. The fact that the question has been so often asked suggests the need for a thorough answer. For back of it there lies a great region of physics and chemistry, a summary exploration of which in the light of the knowledge of today cannot but be interesting. In it are concerned the great doctrine of the conservation of energy, the laws of heat, the three states of matter, and the chemistry of air. And it is not expecting too much of the reader of today to hope that the theory of the subject presented within the compass of an hour's reading will interest him. The account of the liquefaction of gases includes a period of about 100 years, and with it is bound up the history of the Royal Institution of London. In its laboratory Faraday worked with bent tubes, liquefying gases and blowing the tubes to pieces and nearly blinding himself in his efforts. This was half a century ago and more. And now within its walls, with elaborate machinery based upon Pictet circuits of 1877, James Dewar, the successor of Faraday, liquefies hydrogen and helium and ends the century's work. In Switzerland and France, toward the end of 1877, the beginning of the end appeared when oxygen was liquefied. Pictet and Cayetet were the rivals, separated only a few days in their liquefaction of this gas. Discovered by Priestley and Lavoisier almost exactly 100 years before the date of its reduction to the liquid state. America was not idle. Tripler, working away privately, with no institution or association to back him, has surpassed the dreams of the most enthusiastic visionaries and has made liquid air by the barrel, and has sent it all over a wide range of country in tin cans. The long record should not be read until the answer to the query cited above has been given. The reader should know accurately what liquid air is, what constitutes a gas, what the relations of heat and pressure to state of matter are, and how heat is treated by the modern scientist. Matter is generally stated to exist in three forms or states: the solid, liquid, and gaseous. An attempt has been made to assert the existence of a fourth state, the ultragaseous or radiant state. There is a certain objection, however, to this. The first three states are broadly differentiated. As a rule, There is little question of the form or state being solid, liquid, or gaseous. But the ultragaseous state is only recognizable by rather refined tests and may perhaps be better considered as the extreme carrying out of the gaseous condition. Water is the most convenient substance to cite to illustrate the three states. In ice we have solid water. The masses are of fixed contour, and, even if ice is subject to a species of flow, the masses of ice definitely hold their shape. The molecules of solid water are in constant vibration back and forth over the same path, under any conditions of temperature we are familiar with. At the absolute zero this motion would cease. The paths are inconceivably short. We cannot and probably never will acquire any direct knowledge or sight of these vibrations. All we know is that ice at mundane temperatures is hot. It will be seen that, dropped into liquid air, it makes it boil as if the ice were a red-hot poker thrust into it. By the kinetic theory of heat, all hot bodies are held to have their molecules in constant vibration. Molecular attraction holds the particles of the ice firmly together in spite of this vibration. If we apply heat, we diminish this attraction, we increase the repulsive forces, and the ice reaches a temperature where the two opposing forces about balance each other. The attractive ones slightly preponderating. Now there is no longer a powerful set of forces in operation binding the molecules together. They begin to slide about on each other, their vibrations continue with energy, but the paths vary. A molecule bounces back and forth like a billiard ball, recoiling to right or left from its neighbor, so that sooner or later it travels through the entire mass and never ceases its travels. As the molecules slide about without true friction, the ice loses all tendency to preserve its shape and falls to pieces, literally speaking. In other words, the ice melts, and we have water, a representative. The liquid state of matter. Let us apply more heat. Our water is already shapeless. We have to keep it in a containing vessel. Even a drop of water hanging from the window shutter on a rainy day is held in a little sack of water film. Later on we shall see what an important bearing the liquid film has in the manipulation of liquid air. So we put our water in a kettle and heat it. Soon a white cloud issues from the spout, and we may say that we see the steam. If we make such an assertion, it is an erroneous one, as the white cloud is really composed of little balls of liquid water, each held in its own little sack of water film. As the kettle boils harder, we find that the white cloud does not begin its existence until it is a few inches from the mouth of the spout. And a space apparently void of all matter intervenes between spout and white cloud. This space is filled with the substance we are in search of. It is occupied by a column of gaseous water or steam rushing out of the spout and as invisible as air itself. By applying heat to our water, we have made the molecules vibrate through paths many times longer than the old paths. A cubic inch of water gives us approximately a cubic foot of steam. The molecules travel about through the mass with greater rapidity than ever. The mass loses all pretensions to shape or cohesion. A vessel will not hold it unless it is closed everywhere. The third state of matter is formed. The water exists as a gas. By refinement of observation and experiment, most interesting and captivating views are formed concerning these states of matter. Their individual properties are not so sharply cut off and defined as might be supposed. A body is said to be solid when it is practically unchanging in the shape imparted to it. But many solids flow under pressure. The suffering continuous deformation under the action of a continuous force is not a certain criterion of a liquid, but it is good enough to define it or identify it by. A barrel of asphalt opened and thrown on its side in the street seems to be filled with a black solid, yet by the end of the day it will have flowed and changed shape. A stick of sealing wax supported at its ends slowly and continuously bends. Some authorities consider these as examples of liquids. A soft jelly pressed by a spoon yields considerably, but, when the pressure ceases, springs back into its original shape. Jelly, therefore, is treated as a solid. All this seems to cast confusion on the subject. But nothing very critical hinges on the sharp separation of solid, liquid, and gas. It would perhaps be better to assume a continuity of state between solids and liquids, and to consider asphalt, sealing wax, and the like as being on the borderline. If sealing wax is to be considered a liquid, then lead and most other metals could be considered such. For metals, as a rule, are more or less malleable and ductile, and the qualities of malleability and ductility depend upon the flow of the material composing them. We are confronted with the old property of nature expressed in the adage, natura non facit saltum. Nature does not jump. The air we breathe is in the gaseous condition. The water we drink is in the liquid condition. The glass which holds the water is in the solid condition. Yet we can indicate many cases where an intermediate state exists and where a substance cannot well be termed one thing or the other. Even air is not a perfect gas, and hydrogen is an ultra-perfect gas. For want of correct understanding of such things as these, confusion in ideas results and an obscurity bordering upon complication is introduced into our conception of the laws and system of nature. Thus moist air is generally considered heavier than dry air, presumably because a wet cloth is heavier than a dry one. Popularly, people would say that the air is damp and heavy. Now air is wet because of the mixture with it of another gas, gaseous water, or literally steam. Water from rain, from the ground and from the immense evaporating surface of the leaves of the vegetable world assumes the gaseous form and mixes with the air. The specific gravity of water in the gaseous condition is less than that of air. It is about 2/3 as heavy only. Wet air, therefore, is lighter than dry air. A balloon would rise better on a dry day than on a wet day, not only because there would be no moisture with which to dampen the cordage and cloth, and thereby increase the weight, but because the dry air is a better floating medium than wet air, because it is heavier. Wet air is not air soaked like a sponge with water. It is simply a mixture of dry air with gaseous water. The truth is here far simpler than fiction. The sequence followed by a substance in passing from state to state is not always the same, as a solid on heating is often vaporized or gasified directly without passing into the liquid state at all. This occurs in slow vaporization very often. Thus ice in the open air below the freezing temperature wastes away by volatilization and is gasified slowly, without liquefying, and contributes water vapor to the air, although far below the solidifying temperature. Iodine volatilizes in the same way, and those who have used camphor or naphthalene for preserving clothes from moths have observed the same mysterious diminishing of the lumps of preservative used. In druggists' windows the shrinkage of camphor there exposed is sometimes quite striking. Now it is less often exposed than formerly, as naphthalene has largely supplanted it in the trade. Carbon dioxide, the gas which escapes from soda water and other effervescent beverages, when subjected to cold and pressure, liquefies. When the pressure is released and it is allowed to escape into the open air, it solidifies and produces a true carbon dioxide snow. This snow exhibits surprising permanency, disappearing quite slowly in the open air. In disappearing it evaporates and produces gas directly without passing through the intermediate liquid state. Such direct transition from a solid into a gaseous state is termed often sublimation. An expression, perhaps, too limiting, covers the extreme case where a solid on application of heat sublimes vigorously before melting. It is to the effect that the substance boils at a lower temperature than that at which it liquefies, that the temperature of boiling is lower than that of liquefaction. The idea of a solid boiling seems rather odd. It is not only the change of temperature which brings about change of state. Change of pressure affects it greatly. The greater the pressure, the higher is the temperature at which a liquid becomes a gas. A gas just hot enough to hold that form may, under some conditions, be converted into a liquid by applying pressure, without any change in temperature being required to effect the change of state. This, too, is very natural. For a liquid, under ordinary conditions, being of smaller volume than the same molecules gasified, is naturally brought to the liquid condition by mechanical reduction of volume as well as by thermal reduction. Pressure will not always do it, and by combining the effects of great heat and great pressure, conditions foreign to the ordinary status of matter are brought into existence which complicate the problem. Heat is the great and all-controlling agent. Heat is what establishes the critical state, and pressure is quite a secondary matter. For every gas there is a critical temperature and a critical pressure, but the latter is quite a subsidiary thing, and is not critical in the full sense that the temperature is. Pressure tends to liquefy a solid, if the latter grows smaller on liquefaction. So that it is quite conceivable that a point might be reached where pressure would help to convert a liquid into a gas. As such a phenomenon, uncomplicated by other factors, page 24, has never been observed, it is better to set it aside and consider pressure as invariably on the side of cold in liquefying gases. A gas must be pictured to the imagination as a very active thing. In a room full of air the molecules are moving about rapidly, colliding with each other, and bounding about like billiard balls. We know that, if we turn on the gas without lighting it, in a very few minutes the odor of gas will be perceived in all parts of the room. This can only be so because in those few minutes the gas has penetrated every corner. Its molecules have traveled about until some of them are everywhere present, and the activity of their operations may be judged by the amount of gas and the size of the room. An ordinary burner delivers 1 cubic foot of gas in about 10 minutes, and in that time a room of over 1,000 times that volume would be pervaded with it. Hence it will be seen how active the molecules of a gas are. If there were no wind, if the air were absolutely motionless, its molecules would be as active as ever in their own spheres. The air which on one day would be in America would be scattered the next day far and wide. And its molecules would find their way sooner or later all over the world. The same is true in a lesser degree of liquids. The water of a tideless, currentless lake is in molecular motion. The water which beats against the coast of America is in constant process of change, and its molecules are changing and moving about all the time. Sooner or later some of them will be in the waves which break upon the Irish cliffs and English beaches, nearly 3,000 miles away. They would travel thus were there no oceanic currents and no waves. This molecular travel is termed diffusion. We have seen that the motions of the molecules are increased in vigor by heat, that, if heat is withdrawn, they decrease in intensity. The obvious question arises, what would happen if there were no heat? The molecular motions would cease, and molecular death would ensue. The passage of a substance from the solid to the liquid state or from the liquid to the gaseous state involves generally a change in dimension or size. And in the case of many substances the liquid state is the one of smallest size. This is the case with water. In round numbers, a pint of water gives nearly a pint and 2 ounces of ice, if it freezes, and if converted into steam, gives nearly 200 gallons. We are most concerned with the liquid and gaseous states. And under ordinary circumstances there is a very great reduction of volume incident to the passage of a substance from the gaseous to the liquid state. It follows that, to produce liquefaction of a gas, the first thing we should naturally try to do would be to reduce it in volume, and the simplest way to do this would be by pressure. Early experimenters adopted this plan. Natura attained pressures of many thousand pounds to the square inch, yet gases compressed to a small fraction of their volume stayed gases and refused to yield. At last Andrews, of Belfast, made his classic discoveries, and the existence of a critical state was established. This state is very easy to understand. It depends on the fact that for every gas there is a temperature called its critical temperature, and a corresponding pressure called the critical pressure. When hotter than this temperature, no compression, however great, will liquefy it. Below this temperature, a compression easy of attainment is enough to effect the change to the liquid state. The critical pressure is a term which is often misunderstood. It may be said that the pressure is never critical in the full sense in which temperature becomes critical. There is no pressure which can be defined as so low that liquefaction would be impossible in it. There is a theoretical point of cold never yet attained, which is termed the absolute zero. At this point heat ceases, the molecules no longer vibrate, and absolute cold exists. If a body were reduced to the absolute zero, where the motions of the molecules cease, pressure would be without effect upon it, as its only power is to shorten the paths of vibration of the molecules. The term critical pressure is used to describe the pressure required to liquefy a gas when it is at the critical temperature. When a gas is at the critical temperature and at the critical pressure also, the least increase of pressure or decrease of temperature will convert it into a liquid. When in this condition, ready to be a gas or a liquid, it is said to be in the critical state. It will be seen how very well the term critical state applies when a substance is at the critical pressure and temperature. The least change will so profoundly modify its state. A law relating to the critical state is known as Latour's law, and expresses very succinctly the phenomenon of the critical temperature. It is the following. There is for every vaporizable liquid a certain temperature and pressure at which it may be converted into the aeriform state in the same space occupied by the liquid. It will be evident how strikingly this puts the fact that, above a certain temperature, a gas can be squeezed down to the volume of its mass as a liquid without liquefying. If a gas rigorously followed Mariott's law and changed in volume in inverse proportion to the pressure exerted upon it, and if pressure sufficient to reduce it to the absolute volume, as it may be termed, or the volume it should have at the absolute zero, were exerted upon it, it is hard to say what would become of it. The condition of a substance in the neighborhood of the critical state is sometimes termed the intermediate state. The expressions are almost synonymous. The first is the more abstract, the latter the more concrete expression. The reduction from the gaseous to the liquid state is usually a reduction of volume. A cubic foot of steam gives about a cubic inch of water. 800 cubic inches of ordinary air give about a cubic inch of liquid air. But owing to the phenomenon of the critical temperature, or, what is the same thing, to Latour's law, this is not always true. The existence of a gas of no greater volume than the liquid it could be converted into is a sort of scientific riddle. It has its counterpart in the inexplicably great power of expansion by heat possessed by some liquefied gases without departure from the liquid state. The passage of a substance from the liquid to the gaseous state is marked by a change of appearance. A liquid has always a defined limit. It lies in the containing vessel and its upper surface forms a visible boundary. If the vessel is of large diameter, the surface is level and flat, except along the edges, where it curves up or down a little. If the diameter is small, it curves throughout its whole extent, forming a little cup or a little hill, as the case may be. The upper curved surface of a liquid is termed the meniscus. Mercury in a glass tube forms a convex meniscus, water, a concave one. For different liquids in contact with solids the meniscus varies, a characteristic one obtaining for each condition. A very interesting suggestion is due to Germain. It is that when oxygen and carbon dioxide are compressed together, a point may be reached when the carbon dioxide will liquefy but will be lighter than the compressed gas. So that we should have the curious phenomenon of a fluid floating upon a gas. Professor Ramsay seems to think that he has observed this phenomenon. The meniscus in this case lies at the bottom of the liquid and above the gas. For years the disappearance of the meniscus was regarded as marking the change or transition from the liquid to the gaseous state. This view seemed satisfactory. But science is not restful. Doubts began to be cast upon the coincidence of this disappearance with the true transition. Thus in 1892 Zambiasi attacked the problem by experimenting with ether in a sealed tube and reproduced the intermediate and critical state phenomena therewith. Cagniard de Latour's and Cailletet's observations were studied with a more manageable ether. Zambiasi came to the conclusion that the appearance and disappearance of the meniscus, while occurring at a constant temperature for a given tube, occurs at different temperatures in different tubes. The temperature being determined by the relative proportion of liquid to gas in the tubes. In 1893 there were published a number of papers by Ramsay, Galitzine, and others on the subject of the critical state and the uncertainty of the optical method, by simple inspection, of determining the transition from liquid to gaseous state. Quite an acrimonious discussion is contained in successive communications between the opposition scientists. The subject is left rather unsettled. The disappearance of the meniscus with some has lost its old-time definite status, and the case is left pretty nearly in statu quo. But the disappearance of the meniscus is not the only phenomenon of change of state. A peculiar flickering appearance is noted as indicative of it, together with the formation of striae. And so characteristic is this feature that it is used by Pictet in some of his most recent work as an indicator of gasification. If a tube is partly filled with a liquid, is sealed and heated, the first indication of a change of state to be looked for is the disappearance of the meniscus. As it vanishes, the flickering striae appear and a sort of unrest pervades the tube, and quickly the critical state is passed and the liquid has become a gas. The phenomenon is conveniently shown in a sealed tube half filled with ether, as shown in the cut. It is mounted within a larger tube filled with paraffin wax. The latter is opaque and solid when cold, but on heating melts and becomes transparent. On heating the wax, the liquid in the inner tube goes through the critical state, the phases can be watched, and the phenomena described above can be seen. If it is to be shown to an audience, the image of the tube is projected upon a screen by the magic lantern, and the phenomena are produced so as to be visible by a roomful of spectators. The sealed tube is termed Natterer's tube. Hannery and Hogarth, in 1880, in experiments on the critical state of matter, found that several salts, such as potassium iodide and bromide, would dissolve or volatilize in gaseous alcohol at a temperature of 375 degrees Celsius, 707 Fahrenheit, the whole being contained in a strong sealed tube. P. Villard, 1898, extended the scope of this investigation and got very interesting results with solids and liquids. As a liquid, bromine may be cited. This was placed in a tube with oxygen gas, and the pressure was gradually increased. Normally increase of pressure would be supposed to tend to keep the bromine liquid. But, on the contrary, At 200 atmospheres, the bromine began to take the gaseous form and to dissolve in the compressed oxygen. The action of the dark brown liquid was exactly that of a substance entering into solution. The gaseous mixture took a darker color at 300 atmospheres than that of a solution of bromine in water. Villard recalls Cailletet's observation that liquid carbon dioxide dissolves in air. We may also call to mind the liquide Pictet, page 170, this connection. Bromine is a brown liquid, and is one of the elements. Its near neighbor, iodine, is a solid. The latter was found to dissolve in small proportions in oxygen. Formine was another gas which was experimented with. It dissolved ethyl chloride, carbon disulfide, alcohol, camphor, paraffin, and iodine. In some cases, the gas solution phenomena were almost reproductions of the critical state phenomena, including the obliteration of the meniscus. A very interesting suggestion was made by Villard. It was that gaseous solution might take the place of distillation as a laboratory operation. As the doctrine of the conservation of energy is intimately involved in the liquefaction of air and of all gases, something may be said of the relations of force and energy. This may more appropriately be done as it will bring forward a treatment of the subject which may commend itself to some interested in physics. This treatment of the subject is based on the substitution of 2 units for 3. Usually, force, work and energy are the interrelated units appealed to in treatises on mechanics. The far more desirable way is to follow out the theory of dimensions and to take 2 of these units only as the foundation stones of the science. These 2 are force and energy. Work, instead of being awarded an important place, should be treated only as an adjunct and convenient expression of the concrete and accidental. This sounds, perhaps, heterodox. It is really orthodox, and is a move in the direction of avoiding confusion. As music is built up out of a few notes, as the 20-odd letters of modern alphabets in a sense are the basic units of the written languages, so we have certain fundamental elements in natural science. These may, for our purposes, be stated as distance or linear space, mass and time. These are familiar to all. The accepted units are the centimeter, 0.39 inch, gram, 15.43 grains, and the second. Then there are 2 derived units, less familiar in their scientific status, and less generally understood, than the others cited above. These are force and energy. Distance is linear space, space measured along a line, space of 1 dimension. A foot, an inch, a centimeter, are units of distance. An attempt was made to get an absolute unit by taking 1/10,000,000th part of the quadrant of the Earth as a unit. This is what the French meter was supposed to be, but the measurement was inexact, so the unit is as truly inexact as was the old-time barleycorn, except in degree. Its exactness was many times greater, as it approximated at least to a fixed standard, and the length of a barleycorn is as unfixed a standard as could well be imagined, although our system of measures is based on it. 3 barleycorns make 1 inch, and the exceedingly exact standard yard measures carefully preserved by the British and American governments had their origin in the length of a corn of barley. The most recent and scientific unit of length is the wavelength of a given monochromatic light. But for everyday purposes the foot is very generally used in this country. Time is the measure of duration and is the function having a truly international unit, the second. This is an astronomical unit, and might be used as a basis of all others. The proposal to do so has been made, but has never been carried out. Mass indicates the quantity of matter in a body. It is a somewhat unfortunate unit, as it is constantly confused with weight. A piece of iron has a definite mass, but it weighs one amount at the equator and another amount at the poles. On the surface of the Moon it would weigh far less than on the surface of the Earth. From one point of view the proper unit Oi mass would be equal to a pound, or a gram, or whatever may be taken as the unit of weight divided by the velocity a body acquires in falling through a vacuum for 1 second. As this last quantity varies at different parts of the Earth, it would seem that the unit of mass should in some way be fixed, and that the unit of weight should vary. Accordingly, the quantity of matter in 1 gram is taken as the unit of mass. Weight varies, for a pound of sugar at the poles is slightly greater in mass than a pound at the equator. This is very scientific, but does not square with the relative sweetening power of the 2 pounds. We have just spoken incidentally of velocity. This is a unit which indicates the distance passed over in a second. As 2 unitary quantities, time and distance, are involved, it is compound. We are now ready to see what force and energy are. They are the hardest of all to grasp. Had Faraday and a host of others grasped their significance, the erroneous doctrine of the conservation of force would never have been invented. Force may be variously defined. Newton's definition of it as given by Daniel is a measurable action upon a body, under which the state of rest of that body, or its state of uniform motion in a straight line, suffers change. But force may be exerted without producing any such change, so that the definition, like many others, is not satisfactory. A copying press applies force to the book it squeezes as long as the screw is left turned down, but it imparts no change of state of motion or of rest to the book. A spring held by a catch of any kind so as to be in a state of tension exerts force against the restraining piece, but there is no question of change of state of motion or of rest. The definition of force as that which exerts a pressure or a pulling stress upon anything, or between any two or more masses, is, for ordinary purposes, an exact enough definition, though not a very elegant one. The total forces exerted in the universe may vary constantly in amount. There is no such thing as the conservation of force, conservation meaning, in such a connection, constancy or invariability of quantity. Force may be called into existence and annihilated at will. It varies ad libitum just as motion does. A man may run or walk or stand still. He thereby creates or annihilates motion. He may do the same for the force he exerts by his own control. Not many years ago a work was published on the subject of the conservation of force. It was made up of extracts from the writings of various scientists which treated of the supposedly true doctrine of the conservation of force. Among other writers Faraday was quoted, and it is curious to see how he could not reconcile the contradictions of the supposed law. He accepted it on the weight of authority of others. His acceptance giving a lesson in humility which some doctrinaires of the present day might profitably study, all the while the doctrine was an utter falsity and is now discarded absolutely. It is one of the monumental errors of the scientific world. It shows that students of science have their own errors to contend with and guard against. We can reasonably believe, however, that we are not fast bound at present in any such error, at least in the field of physics. Faraday, who has been cited above, was one of the loveliest figures in modern science, and his appearance here is not the only one he makes in the pages of this book. As he appears as one who paved the way for the liquefaction of air and for that of the so-called permanent gases. He it is who gave one of the first blows to this name. There is one survival of the erroneous doctrine which, although it only affects the nomenclature, is interesting to notice. It is the term living force, which cannot be said to have quite disappeared from the language. It was long used as the expression for mechanical energy. The French, who are more conservative than we, adhere to it far more tenaciously, and its equivalent is found in many recent scientific papers in that language. The term is a metaphorical presentation of the idea of force in action, and force in action is nothing more or less than energy. If the action is positive, it is the exertion of energy. If the action is negative, it is the development and consequent absorption of energy. But the best method of avoiding confusion in modern science is to concentrate the nomenclature and to avoid useless multiplication of terms. So the term living force, picturesque as it is very properly abandoned for the more concise term energy. Energy is a unit which expresses the action of a force along a distance. If a man pushes against a car, and all remain stationary, he exerts, properly speaking, no mechanical energy, but only force. But if the car moves, and he follows, pushing it before him, his force is exerted along a distance, and the compound force-distance unit thus indicated is called energy. Two actions are involved. The man expends energy and gets rid of it. It disappears. But the car receives energy, and in the overcoming of its inertial and frictional resistances an amount of energy is received by it precisely equal to that which has disappeared. This energy is largely converted into heat. Suppose an athlete holds a dumbbell by his side and raises it to arm's length. The dumbbell weighing 10 pounds and the lift being 4 feet, he would have expended on it energy represented by the product of force and distance. The force may be popularly expressed in this case as 10 pounds, the dis. Tance is 4 feet, the energy expended is 40 foot-pounds. The energy which he spent in lifting the dumbbell has disappeared, and in its place has been created the energy now inherent in the lifted mass. By virtue of its position the dumbbell has an ability in recovering its old position to exert energy in its own turn. If the bell drops the 4 feet, it will, in doing so, lose its favorable position and exert energy. The exerted energy will disappear and cease to exist. But in its place a precisely similar and equal quantity of energy will be developed. Suppose now that the dumbbell is allowed to fall the 4 feet through a vacuum. At the end of its fall it will be moving quite rapidly and will be able to strike quite a severe blow. This blow it can inflict by virtue of the energy inherent in it. As this is derived from a fall of 4 feet, it will be measured by distance and force as before, by 40 foot-pounds. If it strikes its blow and comes to rest 4 feet from its starting point, its energy will disappear, and in some form or other 40 foot-pounds of new energy will be created. The reader will observe that the dumbbell held motionless 4 feet above its level of rest has the power, when called upon, of exerting in its descent the 40 foot-pounds of energy which the athlete exerted on it. It possesses the power of exerting energy, which power is termed potential energy. Reaching the end of its 4-foot fall, it then is charged with energy real and positive, by virtue of which it can inflict a blow. This is the energy of motion, or kinetic energy. Illustrations could be produced in any desired quantity. It would be found that whenever energy disappeared, an equal quantity of other energy appeared. This law holds good always without any exception, and is universally accepted as fixed and invariable. It is most generally expressed by saying that the total energy of the universe is always the same in amount. It will be noticed that the term work has not been used in this brief exposition. Usually, it is one of the first things cited in such cases, and energy is defined as the power of doing work. But it is much better to keep the fact clearly before us that energy is the important and more fundamental unit, and that work is simply another term for development of energy. To do work is to expend energy. Our athlete, in raising the dumbbell, expends his own energy, develops new energy, and the latter is the doing of work. The particular energy exerted by the athlete ceases to exist, and is replaced by an exactly equal amount of energy developed in the dumbbell by its change of position. The dumbbell, it would generally be said, has had work done upon it, the lifting of it constituting work. It is far more logical to term this lifting the development of energy in the object acted on. It would seem somewhat presumptuous to attempt to do away with the term work, and the word is so convenient, and is in such universal use among physicists, that it cannot be dropped. It should, however, be treated rather as a convenience than as a real physical unit, and it should always be understood to be a shorthand term and synonym for development of energy. If work is performed, it is development of energy that is performed, and the object which does the work expends energy in developing new energy. There is a very simple experiment, which anyone can try, which supplies an excellent illustration of the conversions of energy. An India rubber band is held by the 2 hands across the mouth, so as just to lie between the lips. It is now stretched. The energy of the experimenter is spent on stretching the band. Some other equivalent of energy must be developed to take its place. As the band stretches, the lips can feel it grow warmer. The mechanical energy expended in stretching it is converted into the kinetic energy of heat. It is allowed to resume its original length. In doing so, it exerts energy. It has only the kinetic energy of its heat to call upon. Accordingly, it grows cool as it regains its original length, and the lips feel the cooling effect. It illustrates the law of the conservation of energy excellently, and is particularly interesting to the reader. As it applies very strikingly to the expansion and contraction of gases, we can now appreciate the conception of a reservoir of energy. The pound weight, held at 4 feet elevation, exerts no energy, but does exert force. It is a reservoir of energy in potential form. The same weight, moving with the velocity acquired by a fall of 4 feet, is a reservoir of energy in kinetic form. Brought to rest after its fall, the kinetic energy it was charged with disappears, and it is no longer a source or reservoir of energy when energy is expended by any mechanism. The new energy developed to replace the old in the world scheme, and to keep the amount of the world's energy invariable, is apt to take largely the form of heat energy. A railroad train has expended on it the energy of the locomotive. Suppose it runs a mile upon a dead level. At the end of the mile it occupies a position not one whit more advantageous than when it started, as far as energy of position is concerned. Yet the fire in the firebox of the engine has fiercely burned over the mile run, and the energy of the sun of bygone ages, stored up for geologic epochs in the inert coal, has been expended. What energy has been developed to take its place and keep up the balance? It is energy of heat. The wheels have pounded over the rails, heating themselves and the rails. Their journals and the journal boxes have been heated. And even the energy expended on overcoming the air resistance has heated it a little, and the sides of the cars have been heated a little also. This heat is absolutely useless, or even pernicious. We cannot move a train along a level roadbed, we cannot drive a ship across the level plain of the ocean, without expending energy which we can never recover. It goes into the storehouse of nature, never to be recovered by man until another great step in advance is made. The liquefaction of air has in it a germ, dimly recognizable, which may enable us to utilize the low forms of energy with which nature is charged. The ocean path, and the steamer which traverses it, at the end of the Atlantic trip may have received 140,000 horsepower days of energy. Now it is all lost to man. Man's ingenuity perpetrates no more wasteful and unsatisfactory acts than the transfer of himself and his possessions across the ocean or over continents. The 30,000 horsepower engines of the transatlantic liner are no more a triumph of human ingenuity than in their enormous wastefulness of practically 100%. They are a concession to his inability to utilize the energy of the universe. This brings us face to face with the doctrine of entropy. We have seen that the low degrees of heating produced by the friction of machinery, and which represent its wasteful resistance, are lost forever to us. The potential chemical energy represented by the separation of carbon and oxygen is the energy of carbon or coal which can be burned under a boiler when it unites with the oxygen of the air. This is one of the world's energies which can be utilized by man, and these energies are called available energy or entropy. The world's coal is being burned up, its forests are being destroyed, machinery is adding to the irreclaimable energy of the world, and, by the doctrine of the conservation of energy, is destroying that same quantity of available energy. Hence the entropy of the universe is becoming smaller day by day. Clerk Maxwell saw the possibilities of the utilization of the unavailable energies of the universe. It is provoking to know that our great ocean of air is pulsating with molecular energy which we do not utilize. Yet we do utilize it in a sense in compressed air motors. We call upon it in liquid air work. And Clerk Maxwell's dream of the utilization of the lost energies of the universe may yet come true by the application of liquid air and liquefied gases to motors. A popular paradox, which has been much discussed, may be used to give an example of the doing of work at the expense of the low-grade heat of the air and of other matter. A steel spring is placed in tension or is wound up. It is then dissolved in acid. The question is, what becomes of the energy which seems to be present in the spring, and ready for utilization? One theory is that there is present in it no energy which in any way is due to its being wound up. When first wound, the energy expended in the operation develops new low-grade heat energy, and the spring is slightly heated. Then it loses the heat in a few seconds, and there is no longer any more energy in it wound than unwound. Therefore, it dissolves in acid without having any special energy to account for. Now, the question may be asked, how can the spring, if it has no energy, drive a clock? It does this, not at the cost of any mechanical energy due to its tension, but utilizes the low-grade heat energy of which we have been speaking. As it drives the clock it gets cool, and the energy required to drive the clock is represented by this cooling. As air circulates around it, it recovers immediately any loss of temperature, so that no loss of heat is practically discernible. But the clock is driven primarily by the heat of the air, by heat such as is usually treated as unavailable. The India rubber band experiment described on page 32 is an exact illustration of the point involved. Elsewhere the possibility of using liquid air as a substance for the storage of power is alluded to. If this were done, an engine could be driven by it exactly as by steam, except that the heat would be drawn from the atmosphere instead of from a burning furnace of coal. And there would be a utilization of low heat energy.